Okay, Elizabeth, I'm going to begin. Okay, so welcome everyone. This is really a special personal pleasure for me to introduce one of my fellow Canadians, Allan McDonald. So Allan grew up in Antigonish, Nova Scotia. Antigonish is a small town which is most famous for being the home of St. Francis Xavier University. The population of Antigonish is 4,364, which I believe, Allan, is fewer than the number of students at the university.
Around the same.
Before the European settlers came, Antigonish belonged to the Mi'kmaq First Nations tribe. And Allan, by an incredible coincidence, behind my head is a portrait by a First Nations painter of a Mi'kmaq woman from your area in Nova Scotia. Complete coincidence.
Very cool.
Yeah, very beautiful painting. So Allan then was an undergraduate at St. Francis Xavier, which Americans probably don't know, but every single Canadian knows as really the finest undergraduate, or arguably at least the finest undergraduate college in Canada. He then went from there to the University of Toronto, my own alma mater. And he has a particularly charming statement online in his personal statement at the University of Texas, and I'll read it to you. He said, "I chose physics because my girlfriend at the time, now my spouse, worked at a hospital attached to the University of Toronto's downtown campus that was across the street from the physics department. It turned out to be a doubly good choice for me." I particularly like that because I went to Yale and did a PhD in physics rather than going to MIT and doing operations research for exactly the same reason. So many of us find very strange reasons for ending up in physics. Allan, of course, I mean, is familiar to all of us, has made an incredible range of contributions. He went from the University of Toronto, where he worked for one of my friends, Cy Bosco. From there to the National Research Council in Ottawa. I happened also to work there for a little while. And then he went from there to Indiana, and then from Indiana in the year 2000 to the University of Texas. And he'd already done beautiful research up to that point. But I have to say, Allan, and looking at your CV, there's obviously something in the Texas air that's been good for you, because you've produced just an extraordinary number of profound papers while at the University of Texas for the last 20 years. Includes the anomalous Hall effect, the intrinsic spin Hall effect, photonic topological insulators. And the subject we're going to hear about today is Moiré bands and twisted double layer graphene. Now, some of you will remember the very beautiful colloquium we had by Pablo Herrera from MIT, where he talked about the experiments, but the experiments which he gave generous credit to Allan were actually motivated by theory. So this is one of these cases where the theory was done first and the experiments were done second, which we experimentalists are usually very reluctant to admit. So anyway, so this is just the absolutely beautiful combination of first elegant theoretical predictions by Allan, and then very beautiful experiments by Pablo, which we heard about already. This was very quickly recognized by the Wolf Prize in Physics, which was, I was going to say the culmination. Maybe it's not the culmination. There's one more prize out there. But Allan had already been elected to the National Academy of Science, the American Academy of Arts and Sciences. He won the Buckley Prize, now the Wolf Prize. And so he's been well honored for his many contributions. So today, the title of Allan's talk is Moiré Magic, and he's going to tell us about electrons in 2 dimensions with this very unusual Moiré geometry. Allan.
Okay, thanks, Bob, for that wonderful introduction. I would far rather be visiting you in person. I have many friends at UC Berkeley. So my topic today, as Bob mentioned, is superlattices, Moiré superlattices, this is a topic that I actually started working on a little over a decade ago. and it's a topic that's become much more interesting thanks to experiment, and I'll try to tell you a little bit about it. Please feel free to interrupt me at any time. So this subject had its 15 minutes of fame, as Bob mentioned, thanks to incredible experimental progress that we couldn't have imagined, couldn't have hoped for at the time we started working on this topic. And really the spectacular and surprising discovery that was made by Pablo Herrero, you heard from recently, is summarized by this typical color plot, which emphasizes a couple of important aspects. So this is a way of making artificial crystals. And it's artificial crystals, as I'll explain, with around 40,000 atoms per unit cell, so big lattice constants. And one of the things that's important about having such, big atoms, so to speak, is that you can change the number of electrons per atom just using electrical gates. And so a typical set of experimental data like this one Pablo would have talked about shows carrier density. This is in these periodic structures I'll talk about. This is changing the number of electrons per atom by 1, 2, 3, 4, down to -4 electrons per atom. And over that range, you see insulating states, superconducting states, and we're learning lots more about these states, and that'll be the main subject of my talk. I think this actual data set is from a follow-up experiment by Dmitry Yefetov at ICFO in Barcelona. And one of the things you can see here that's rather amazing is that the number in this 2D system, you go from an insulating state that's in this dark red color to a superconducting state in blue with a change of electron density of around 1 in 10 to the 11 per square centimeter, or around 1 for every 10,000 actual carbon atoms in this system. So this is probably the most lowest dense electron density superconductor in nature. So I'll come back in the second half of my talk and talk about what we know about what's behind this data right now. But the structure of my talk is I'm just going to I'm going to start off saying something about the motivation, why this ability to make superlattices is interesting from the point of view of quantum condensed matter physics. And then I'm going to say a few words about Moiré materials more generally. Some of the most interesting work on Moiré materials, both theoretically and experimentally, is being done on your campus at Berkeley. But the last half of my talk, I'm going to talk particularly about bilayer graphene Moiré superlattices. Okay. Condensed matter physics is kind of an odd subject in the sense that we know everything about our starting point. It's just quantum mechanics and Coulomb interactions, the same things we learned about in high school that describe a periodic or explain the periodic table, for example. But the subject is interesting because becomes more interesting because electrons aren't stuck on atoms. They can move from atom to atom in a crystal. This is an example of a crystal, two-dimensional crystal. This is the two-dimensional crystal that I'll talk about most in my talk. It's a honeycomb lattice. It's the simplest example in textbook of a lattice where there's more than one atom per unit cell, called here with great imagination A and B sublattice. Turns out that all of these points are can be reproduced by translations using elementary translations starting from any two of these sites. And okay, so one property that we all know of crystals is Bragg scattering. And what Bragg scattering tells us is that momentum can only be changed in discrete units in a crystal by scattering off the crystal. And what that means, it has profound implications for solid state materials, of course, because it means that just like particles in free space, momentum is a good quantum number. Only a good quantum number modulo reciprocal lattice vectors, but in many ways, electrons in a crystal share the properties of particles just moving without any potential in free space. And that's why we can have states that can carry current, that have a velocity, and why the conductivity of metals is so large, and so on. So, if this was the story of condensed matter physics, it might be that we would have stopped some time ago, but it's not. So it turns out that electrons moving through a crystal will often run into each other, and when they do, they interact, and then you can no longer treat the electrons as independent particles, and then the quantum mechanics becomes, as we all know, exponentially, with quantum information, exponentially more complicated. And with two consequences. One is that very often we're not very good at really predicting the properties of a crystal, even when it's rather simple, which you might think is a humbling consequence. But another consequence is that the quantum mechanics of electrons in crystals, which are, in some sense, almost free particles, but particles that interact with each other, can very often yield experimental surprises that are not anticipated theoretically. So, and the imagination of nature is much greater than the imagination of most of us. And so that property, that surprise is possible, is what keeps the subject lively. And there's one particularly perplexing problem that will figure into my talk today. And that's the problem of high temperature superconductivity that occurs most famously in copper oxide crystals, cuprates. And so achieving a full understanding of cuprate superconductors has been a tremendous challenge for quantum condensed matter physics for a long, long time. And even though much is understood, much remains ununderstood. This problem is so fundamental to quantum condensed matter physics that people have contemplated very roundabout ways to learn something about this system. And high temperature superconductors in many ways have extremely simple electronic structure with mainly one active band that's partially filled with electrons. And that system can, in principle, be realized by making an artificial crystal of fermion atoms and cooling them to extremely low temperature. And this is something that has been attempted, is still being attempted, but is rather difficult, it turns out. And so what I'm going to say is, there are two main messages of my talk. Maybe the first one is that we can simulate quantum matter with this new type of artificial crystal I'm going to tell you about. And the second message is that this one particular example on which I will focus, two graphene layers twisted relative to each other, has much in common with cuprates. And I think this is becoming more and more clear as time goes on. So let me turn to my second section. I'm going to just make a few general remarks on Moiré materials for those of you who haven't followed this. So one thing I learned when I first saw the word Moiré, which I maybe should have known earlier, but it was in this connection, is that according to Wikipedia, at least, the word moiré is connected to the word mohair for a type of wool, particularly handsome type of sheep that produces this very wavy type of wool. But moiré is a well-known technical term in electron microscopy, and refers to these slow spatial changes in the registry of one layer relative to another when two layers with regular patterns are overlaid. And so these moiré fringes are very familiar, and one of the first things people saw in materials when they started doing, for example, scanning tunneling microscopy. And but there's a particular type of moiré pattern that is relevant for moiré materials, and it's one that occurs very naturally when you have two-dimensional crystals. And this is a subject that emerged out of the subject of two-dimensional crystals like graphene, the ability developed over some time, starting with Andrei Geim and Kostya Novoselov, to separate and isolate and stack, which is important here, two-dimensional layers of material extracted from very anisotropic three-dimensional crystals. So what's on my slide now is actually a honeycomb lattice that I showed you before, but it's actually two honeycomb lattices, one on top of the other, with gray lines drawn between the lattice points. You only see one of the honeycombs because they're right on top of each other. But when you rotate one relative to the other, you can see this very important property of moiré materials, that you get a spatial pattern on a longer scale of the registry between the layers, and you can control the periodicity of that pattern just by controlling twist angle. So for the systems I'm going to talk about, it's nearly, for all practical purposes, it's exactly true that the quantum mechanics we're interested in is determined only by that larger scale moiré periodicity, and the atomic scale periodicity is not seen. So that's how they behave as artificial crystals. And so let me start with what is the simplest, the simplest example of a moiré, what I call a moiré material, which is not the one we looked at first, but it is the simplest. And it's formed by overlaying two-dimensional crystals that are different from each other. The two-dimensional crystals in this case are semiconductors, two-dimensional semiconductors, and in particular, this is the example of tungsten diselenide on molybdenum diselenide. And these two materials have nearly identical lattice constants. You can also look at tungsten diselenide on molybdenum disulfide, or it would be quite similar. And so this is in TMD hetero bilayers. Hetero bilayers means the two materials are different. And so if you just make a few holes, that's the case that has been studied most often in the valence band of this bilayer, all of those holes will go into one of the two layers. And therefore, near the Fermi level, there's basically only one state for each momentum that is near the Fermi level. And so when you form a Moiré pattern, like I was showing you for the graphene bilayer case, every property depends on the registry between the layers. And here, since we have only one state at momentum, the only thing that can change with position is the energy of an electron with that momentum. So it turns out that in the Moiré structure, you have a model in which the You have holes in the valence band with an effective mass that reflects the curvature at the top of the valence band, and they experience a periodic potential with the periodicity of the Moire pattern. And so this is a very simple artificial crystal. It turns out that actually I lied. There are two momenta, but they're far apart in momentum space. We'll refer to them as valleys. So there's two different regions of momentum space that can be active, but because of spin-orbit coupling, there's only one state for each spin, and because spin is locked to momentum, it turns out that this problem maps exactly to particles with spin in a periodic potential. And the size of the potential is 30 MeV. For a typical twist angle, the period is something of the order of 10 nanometers. So you've basically mapped real crystal physics from the EV scale to the 10 MeV scale, and from the 5 angstrom lattice constant scale to perhaps to 10 nanometers or so. So I won't have time to talk about this, but there's a lot of interesting work, much of it done at Berkeley, being done on these basically two-dimensional Hubbard model systems. And a number of papers last year. Turns out to be a very attractive thing that you can probe these two-dimensional Hubbard model systems optically. And that's enabled people to do a lot of interesting work. The figure on the right is actually an optical measurement of the basically spin susceptibility of a two-dimensional Hubbard model as a function of the number of electrons per period of the crystal. And by doing similar experiments, people have demonstrated that lots of different correlated insulator states occur in this system, some not entirely expected. Yet, let me just mention in passing that this first two-dimensional Hubbard model system that people are studying is for electrons on a triangular lattice. We'd really want to do Hubbard model systems that are closely related to high temperature superconductivity, maybe, and and in high temperature superconductors, an important property is that the ground state with no doping, with no electrons present, is a antiferromagnet. It's a collinear antiferromagnet, and in order to get that kind of state, you need to be able to split the lattice into two sublattices. You need a bipartite lattice, and it turns out that you can actually get bipartite lattices in. You can get a two-dimensional artificial honeycomb lattice. This is at least theoretically by by making a homo bilayer system of a particular type, where the two electrons in the two layers hybridize so strongly that they combine to form, in effect, a single layer. And so let me actually skip that. So I hope that example will be studied more in the future. So now I'm going to turn to the last half of my talk and talk about what is called magic angle twisted bilayer graphene. So it's a Moire superlattice formed by twisting two layers of graphene, one relative to the other. And a magic angle is a word, perhaps a bad terminology, that I invented some time ago, and maybe it turned out to be fortunate terminology. So let me go back to graphene. This is single layer graphene, and this is energy as a function of momentum. This picture allows me to emphasize a little bit more what I've been saying before. Energy, the region of size of momentum space because of Bragg scattering is finite in a crystal. It's called a Brouin zone. And it turns out, like in the TMDs, the active momenta are near the corners of the Brouin zone. And there are two such active momentum, usually called valleys, related by time reversal symmetry. And low energy states have momenta near these Brouin zone corner points. And so this means all of the low energy states have practically the same momentum. And that means that they cannot see, their ability to resolve space is limited by, 1 over the range of momenta by uncertainty principle that is available at low energy. And that doesn't allow them to see whether a system is actually commensurate or incommensurate at the atomic level. Only the longer distance Moiré periodicity is seen. So here's graphene bilayer. For each momentum in a graphene bilayer, or if there are two states for each momentum near the Fermi level in a single layer, obviously there are 4 states in a bilayer. And this is actually a plot for the thermodynamic equilibrium structure of a graphene bilayer, which is called Bernal stacking. You can see here that the low energy states in this spot are all close together in momentum space. So that means they're described by a Moiré, a model with Moiré periodicity. And you can also see that there are 2 states that are especially low in energy. They actually touch here at what is 0 momentum if we measure it from the Brouin zone corner. And there are 2 other states that are pushed away in energy. And because there are 2 layers and 2 sublattices in each layer, you would have expected 4 low energy states, but it's the Hamiltonian splits out 2 of them. And something very similar is going to happen when we have a twist angle. So we can describe the electron waves in this energy range as a linear combination of an atomic orbital centered on these different sublattices, top and bottom A and B sublattices, and the coefficient of those waves, a coefficient of those atomic orbitals very slowly in space. And so the single electron wave functions are defined by 4 component spinners, which are the components of these 4 sublattices. So this is the kind of object that exists in the quantum mechanics of these systems. And so this is going back to work with Rafi Bistritzer. People were actively looking at the properties of graphene bilayers around this time. A lot of the focus was on actually the commensurability, which occurs at a certain discrete set of twist angles. And much of the point of this paper was explaining, or arguing at least, I see Lin is there, so I don't want to say anything is rigorous.
Oh, thanks.
So much of this paper was arguing that you would never be able to see atomic scale periodicity at small twist angles, that it would really give very small, essentially unobservable effects. And that the right way to think about it was that you have a Hamiltonian, which involves these 4 different sublattices I was speaking about, and that the way the layers couple to each other is from tunneling from one layer to the other, and that tunneling would have show the spatial periodicity of the registry between the 2 layers. So we knew, very people from the graphite literature know what happens if you have 2 layers of graphite and you stack them one on top of each other. That means you only hop, in the same sublattice. But if there's, for example, Bernal stacking, then it's only one sublattice of one layer can only tunnel to the other sublattice of the other layer. And so when you have a Moire pattern, this interlayer tunneling amplitude slowly varies as a function of position. I'm plotting here, for example, the tunneling amplitude from the B sublattice of one layer to the A sublattice of the other layer. Complex number, of course, that, and the main point of it is that it has a simple spatial structure which simply reflects the registry between the two layers, which is slowly changing in the Moire pattern. So in this way, you can have a model Hamiltonian. And the magic thing that happened, which we didn't tried very hard, but didn't really fully understand at the time why this happens, is that at a discrete set of twist angles, the lowest energy states go extremely flat. The velocity of the electrons at zero energy goes through 0. And the typical velocity of electrons in these bands is reduced by a factor of more than 100 relative to the electron velocity in graphene sheets. And we know when we slow electrons down, then their physics will be controlled by electron-electron interaction. So that was already obvious of this at this time, and but was not obvious. What was not obvious at all is that it would be possible to actually prepare 2 graphene sheets with this magic twist angle, and that's what was achieved experimentally. Actually, with this motivation, as Bob said, by Pablo Herrero and other people made steps towards establishing that ability. Okay, so at a magic twist angle, you get very slow electrons. And I want you to notice here that in our calculation, these other bands, which I will refer to as the remote bands, aren't so remote at one particular momentum in the Moire-Bruin zone. And so it turns out that that is an artificial property of our model that I won't have time to explain in detail, but improved models, these remote bands actually do move away. So this is one of the important aspects of the way in which the electronic structure models have improved over the years since this work. And it's critically important in the actual phenomenology. Okay. So I'm going to, so Bob, when should I stop roughly? Okay, you were muted.
Thank you. Another 20 minutes.
Okay, very good. Okay, so one of the important properties of these flat bands that are in magic angle graphene is that they have non-trivial topology. A lot of this has been clarified by other people, maybe especially the group of people around Ashvin Vishwanath. And but I'm going to explain it in terms of analogous physics that occurs in a simple AB Bernal bilayer. It turns out that many properties of AB Bernal bilayers get echoed in twisted bilayer graphene, but with an extra element that makes it even more interesting. So this is a plot on the left-hand side of wave functions as a function of momentum. The low energy states in a graphene bilayer are a linear combination of a component in one layer and a component in another layer, as I guess Eli first taught us many years ago. And what this plot shows is that the wave functions are, in this block sphere representation, are a linear combination of a part in one layer and a part in the other layer, and that the phase relationship between the components in the two layers winds by 4 pi when you go around a circle in momentum space. So this is obviously this momentum space winding of the block states is related to the Berry phases people discuss, and it's obviously topological, and but it is also not a very happy configuration of states for electrons. So just like we're used to thinking about in connection with magnetism, because of exchange properties in quantum mechanics, it turns out, as is manifested in magnetism, that its energies are lowered by making nearby states in space have the same spin orientation. Turns out, at least for long-range interactions, and I'll come back to this in a moment, same thing is true in momentum space. The energy is lower if you can make all of these block sphere layer pseudospin states, ones that are close together in momentum space, to be close together in wave function. And indeed, the ground state of bilayer graphene, if you make the interactions strong enough by actually removing the dielectric material around them, the interactions will prevail and open up a gap. And so this is what the gap states of the broken symmetry state look like, and what the wave functions do to effectively make a core in this momentum space vortex is they spontaneously turn around, twist around so that they're localized in one layer or the other. So you can imagine this block sphere of pseudospin states for the layer pseudospin states. If you cover an area in momentum space, it will cover an area on the block sphere. And that's the property of basically the Berry curvature or the Berry phases, as you might know, are related to how much area on this block sphere is covered as you move around momentum space. And so this says we have large Berry curvatures in momentum space once we break this symmetry. And in fact, if we integrate over momentum space, it turns out that the integral is quantized. And through the grace of God, it turns out that this topological object, this this topological characteristic of electronic states, this particular one is actually something you could measure. It's the Hall effect. So this state with this structure in momentum space gives a non-zero Hall effect, an anomalous Hall effect, a Hall effect without a magnetic field. And so now I have to complicate the story a little bit and admit that there are 4 groups of such state, distinguished by the valley I was speaking about, which of the 2 momentum regions the states are located near. And also there are 2 spin states labeled here as spin up and spin down. And those can, as indicated in this cartoon, those can be layer polarized. Each of them can be layer polarized more or less separately. And so for example, state B in this cartoon is a state in which, maybe I should do this one first. So state A is a state in bilayer graphene that's easy to generate experimentally simply by applying an electric field. So you push electrons from one layer to the other so that they're mostly in the top layer. And so in this state, all of the states in both valleys are polarized to the top layer. But as shown indicated by these arrows, that actually means that they have opposite chirality, opposite Berry curvature, and opposite contribution to the Hall effect. So when the wave functions in the two valleys are polarized in the same way, then you don't get a net Hall effect. The Hall effects cancel. The ground state, it turns out, is actually an antiferromagnet, state C here. But what you see in experiment is that this state, where you have a quantum anomalous Hall effect, even though it's not the ground state, it appears if you apply a little magnetic field to stabilize it. And all of these things occur also in twisted bilayer graphene, but you don't have to remove the dielectric, so it's much easier to get at experimentally. And there's another important change, which is summarized on this slide. So this is a cartoon of the flat valence band in blue and the flat conduction band, the two flat bands. There are four of them, one for each spin, one and valley. And what I've said so far is that you can open up a gap between the valence band and the conduction band. And when you do, you get a Hall conductivity. But the thing that's different with when you have the Moire superlattice is that you can also have a put the Fermi level in a gap by, for some spin and valley, completely emptying the flat bands or completely occupying the flat bands. And because the flat bands are so narrow, as I've showed you before, it turns out you can easily do this and break these symmetries and have different filling factors for different flavors. And so in this way, you can easily get a net Hall conductivity. For example, if only one of the four valence bands is occupied or only one of four is empty, you will you only get a contribution from one valley, and that is expected. That can be understood that will give a quantum anomalous Hall effect. And indeed, this was quickly seen in this subject and seen in experiments from Aaron Sharp, from David Goldhaber, Gordon's group and collaborators. And they saw a very large anomalous Hall effect in this system that could be changed in sign. And now this quantum Hall effect has been shown to be nicely quantized, and I think it will turn out to be perhaps our best experimental example of the quantum anomalous Hall effect. And yeah, so I'm going to skip one thing here, but let me just mention in passing, what's really going on in this quantum anomalous Hall effect is that extra electrons or holes that I'm putting in this system are choosing to occupy one flavor only. And this is actually an example of what Heisenberg and London in the 1940s put forward as a theory of superconductivity. It's an incorrect theory. They thought that electrons in a crystal would spontaneously reorganize to occupy contiguous regions of momentum space, and that this could give a current. Doesn't give a current, it only gives a circulating current, orbital magnetism, but their reason for this is more or less what happens. They argued that states close together in momentum space have large exchange energies when you have long-range interactions. And this idea that they put forward is really what drives this spontaneous valley polarization, or what London and Heisenberg called momentum space condensation. So the properties of these quantum anomalous Hall systems are interesting, and it's interesting to compare them, but I'm going to skip this part and end with what I promised you at the beginning, which was to say that there are very deep similarities in some of the most interesting properties between magic angle twisted bilayer graphene and cuprate superconductors. Obviously, they both have superconductivity, and they both have Fermi surfaces that you can see with different kinds of probe, photo emission for very famously for cuprates. In the case of magic angle twisted bilayer graphene, the Fermi surface is revealed by Shubnikov to Haas oscillations, magnetic oscillations, most of you are familiar with. This is a usual plot at some temperature of resistivity as a function of carrier density, which can be tuned through this entire range, and magnetic field. And as most of you know, these oscillations up and down of the resistivity reflect Landau levels passing through the Fermi level, and you can read off from these the size of the Fermi surface. And what that tells you is that there are, in this region of density, and the density, of course, is exactly known from the gate capacitance. In this region of density, there are 4 Fermi surfaces, as there should be because of the spin and valley degeneracy. And they're exactly degenerate, and they have a Fermi surface, and nothing special is going on here. But here's another way to measure carrier density. This way of measuring carrier density is used in many different materials, of course. It's measuring the Hall density. This experiment data is from the group of Andre Young, but there are many other data sets in literature that are very similar. Again, this is showing filling factor as a function of density, and the Hall resistivity is 1 over the carrier density, as you remember from elementary solid state physics. And so this is 1 over the Hall resistivity, which is a measure of carrier density. And this is the region of filling factor, Moiré band filling factor that I was pointing to before. Here, filling factor is measured from 0 to -4 for the valence band, because there are actually 4 bands, and 0 to +4 for the conduction band. And what you can see here is that the density is changing linearly, just as it should. And this is perfectly consistent with the Shubnikov to Haas measurements. And but then something happens near -2, and that something happens at an even lower density on the electron side. So what is that something? So first of all, here's a theoretical calculation of the same thing, of the Hall density. This is just Boltzmann transport theory and relaxation time approximation. The reason people measure the Hall resistivity is because in the relaxation time approximation, at least, it's a pure band structure property. The scattering rate cancels out. And this is our original band structure model. And these are some improvements on this band structure model I won't discuss, but you can see they're different. And this is maybe the best of this band structure models. There's a big particle hole asymmetry. But what you find if you calculate the Hall density is that on the electron side, it should be electron-like until you reach a Van Hove singularity, and then the constant energy surfaces become Hall-like. And on the valence band side, exactly the opposite thing happens. Okay, so this is not at all like what is seen experimentally. Instead, the Hall, if I focus on the Hall side, the Hall density doesn't change. It just jumps back to 0. And so it jumps actually by 2 units. And so what is going on, I believe, and I think this is probably the picture most people in the field have, that as you make holes in the valence band, the bands are very narrow. You're approaching a region where the density of states is even higher, and the system reorganizes by emptying 2 of the 4 bands, and then it starts emptying them again. So these are jumps which are huge Fermi surface reconstructions, which completely eliminate some pieces of Fermi surface and shift the total carrier density by 1. Okay, so I think I'm running out of time, but I just want to make this analogy. I'm going to say exactly the same thing happens in the cuprates, and it's one of the important pieces of the phenomenology. This is a plot. This is actually a kind of a phase diagram of cuprates, high temperature superconductors. You've probably seen many of them. This particular one was assembled in a recent paper by Louis Taillefer's group. And I think this is all bismuth, bismuth 2212. And in this version of the phase diagram, you have a superconductor, you have the antiferromagnetic state with no doping, and there's a large region of temperature where so-called pseudogap phase, where there are hints that there's suppressed occupation of states near the Fermi level in various different quantities. And the point that Louis is trying to make in this work, and he would argue that it happens in all of the cuprates, is that somewhere on the so-called overdope side, when TC is going back down, the pseudogap line joins with the superconductivity line, and just at that point, the Hall density jumps by 1, and as if on one side of that line, the Hall density looks like you're actually in a doped antiferromagnet. And on the other side of the line, it looks like you have all of the bands available. And, I talked about these Fermi surface reconstructions in magic angle twisted bilayer graphene in the language of mean field theory in 0 temperature. In fact, we know that there's no long range spin order in this system because there's practically no spin orbit coupling. So there's nothing to give magnetic anisotropy, which is absolutely necessary in 2D. So you certainly, even though we can't do a neutron experiment, unfortunately, we know that there's not, we don't expect that there's long range order of these spin and valley pseudospins in magic angle graphene. Instead, in fact, we have a pseudogap phase, and these jumps in Hall density are exactly the same jumps that are occurring in the cuprates, and they're where they occur is always very close to where there's superconductivity. And so should I stop now, Bob? That might have been yes, but I didn't hear it. You're muted.
Keep forgetting to unmute. Well, if you can wrap up now.
Okay. Yeah, so I won't discuss this in detail, but the resistivity is also strange, hard to understand in terms of Fermi liquid, especially near these jumps in Hall density. And this, you can calculate what the resistivity would look like as a function of temperature. If you had simple phonon limited resistivity, what happens is the resistance gradually goes down as you make the Fermi surface bigger. This is actually calculation is on the whole side. That's not at all what happens experimentally. Instead, as you put in more carriers, the resistivity goes down. But then as you approach this region where the Hall density jumps, it starts to go back up again. And turns out that especially on the electron side, you really see regions of, this is just replotting data published by Andrea Young's group in Nature Physics in 2019. But you really see non-Fermi liquid temperature dependence of these quantities. And so I'll stop here. And just to summarize briefly, Moire superlattices both give us a route to really, I think, simulate important, simulate real crystals with whose properties we want to understand better. And it gives us a new route for understanding them better simply by measuring them. But also it gives us some new problems in quantum many-body physics. And in particular, magic angle twisted bilayer graphene has on top of strong correlations, it has this topological properties that give you the quantum anomalous Hall effect seen across the bay in Stanford for the first time by Goldhaber-Gordon's group. And at the same time as it has that topology as a unique new feature, it seems to have these large Fermi surface reconstructions, changing Fermi surfaces by large areas, and seemingly critical behavior associated with these changes of Fermi surface area that have been hard to understand in cuprates and are hard to understand here. But hopefully we'll be able to do some new types of experiments which will give us a new angle on trying to understand what's going on. So thank you very much.
Thank you. This was just spectacular. Let's see, with 100 people, it's going to be hard to monitor questions. So I'll just ask people to just start and ask. Let's just do it empirically and start. If you have any questions, go ahead. But you have to unmute first.
Marvin, looks to me like you're speaking, but you seem to be muted somehow. Still not got it.
Okay, while we wait for Marvin, let me ask a question then. Oh, here he is. Go ahead, Marvin.
Are you guys getting it?
No.
Yeah, okay.
Okay.
So
let me ask a question then while we wait for Marvin. As you know, the two-phase phase diagram, in addition to what you showed from Louis Taillefer, is extraordinarily rich. And in the underdoped region, where there's the pseudogap, there's also very complicated and elaborate charge density order. And there's spin glass order at low temperatures as well. Are there any parallels in the Moire systems?
One of the surprises in the TMD Moire systems, maybe I think seen first at Berkeley, is in Feng Wang's group, is the fact that there are other there are other density wave order at smaller rational filling factors. Those have not been seen and in twisted bilayer graphene. Incompressible insulating states have only been seen at integer filling factors, but maybe they're there and they just haven't been seen yet. You know, one of the things I should have emphasized more is it's just incredible experimental accomplishment. If you look at the resistivity curves that I showed you, you know, there are resistivities that are less than the quantum of resistivity by factor of 20 or so, or even 50. And that means the mean free path is 50 times the artificial lattice constant, 50 times 10 nanometers. And it's only because you can have mean free paths that are very large on the 10 nanometer scale that you can see all of this intrinsic physics. So it seems like, you know, people haven't intentionally made samples dirty. That could turn out to be an interesting angle because it might indeed give rise to some informative glassy phases at low temperatures.
Allan, can you hear me now?
Yep, perfect.
Okay. I assume that the superconductivity is caused by pairing. Could you say something about the mechanism?
The mechanism is not really known at the moment. It could be phonons. If there were no Coulomb repulsion, phonons would be strong enough to produce the observed superconductivity. But you know, where the superconductivity occurs is close to the regime where these unusual fluctuations in the collective, in this case, it's not just spin, it's spin and valley and also orbital degrees of freedom are occurring. And I think that it's very likely that the superconductivity has to do with that. And, you know, one version of this that Mike Zillital in your department, along with Ashvin Vishwanath and other Kalef and others at Harvard have explained, is a very, very attractive picture in which the charged particles are actually skyrmion textures in the magnetic order parameters. And the fact that those textures in the magnetism actually carry charges is, of course, connected to the topological character of the bands. So I would not be surprised if something of that sort turns out to be the case, and hopefully we're moving towards understanding that, but perhaps not completely there yet.
Are these S-wave superconductors?
You know, so I don't think that is known. I think actually, you know, the common picture is that the pairing occurs actually in a ferromagnetic state. So there are, you know, so they're spin triplet, but there's also this valley degree of freedom. And in that case, they would be, you know, they would be valley singlets. And because valley acts so much like just a pseudospin label, except for the electron-phonon scattering, of course, then, you know, it behaves very much like a singlet, a spin singlet superconductor.
Have there been magnetic field studies?
Yep. So, you know, critical field is a couple of Tesla. And it seems if you, so.
Is it type 1 or type 2?
It's type 2. It's type 2. I mean, but, you know, nobody's seen a vortex lattice yet.
That was my next question.
Yeah. So, you know, it should be possible if you to see a vortex lattice. I'm not sure why it's not been done. It seems like, you know, scanning probe with the right kind of spatial resolution there is this Moire periodicity on a 10 nanometer scale. The magnetic length, or distance between vortex cores at 1 Tesla is not so much bigger than that. So the vortices should be very strongly pinned. And in terms of the effective lattice constant of these systems, the HC2 occurs, the coherence length, if you like, is very close to a lattice constant, a Moire lattice constant, just a couple of Moire lattice constants. So, but that's certainly something I'm extremely interested in, and I'd be very interested in chatting with anybody who thinks they know how to attempt such an experiment.
Well, maybe someone could sprinkle iron particles on it.
Yes.
That works in a 3D system.
Yeah.
Okay, we're running out of time. Are there other questions? Do you want to speak up? Okay, if not,
Okay.
thank you so much. This was just an absolutely beautiful talk.
So thanks to all of you for listening. It's certainly been my great pleasure, and I hope to see you all in person before too many more months have passed.
Great. Okay, bye-bye.
Bye-bye.
Bye.
Bye.